Okay, so I'm going to dim the lights down. Okay, so let's take a look at this number sense part 1. Number sense is the name of the unit. It's a unit in the Manitoba math curriculum. And today we're going to be looking at this idea of rational numbers. So the first thing I'm going to do is I'm going to show you what I'm supposed to teach you. This is what every grade 9 kid is supposed to learn. This is right out, this is sort of math teachery talk. But this is what it says you guys should learn. In the number sense unit, and it's not in order, but generally you're supposed to know this. You're supposed to demonstrate an understanding of rational numbers by comparing and ordering, putting them in order, rational numbers, solving problems that involve arithmetic operations on rational numbers. Specifically, put a set of rational numbers in order, whether in fractional or decimal form, and placing them on a number line, either vertically or horizontally. Identify a rational number that is in between two rational numbers, and solve a problem involving operations on rational numbers in either fractional form, decimal form, or a combination of rational forms. So this is what it actually says in the curriculum. So what I'm putting this up here at the beginning. We just took a look at it. We're going to try and figure out what that means. And at the end of this presentation, we'll just go back to this, and hopefully you guys will feel confident that you kind of understand what all that means. Some of you might understand it now. Okay, but before I get started, we're going to just do a little bit of philosophy here on mathematics in general. If someone asked you, what are you the most certain of in the whole world, right? Like, you might answer, my name is Dave, right, or something like that. But a lot of people use mathematics as one of the most certain things they can say. They can say, like, 2 + 2 = 4. I'm certain of that, okay? So mathematics seems to have a lot of certainty in it. We talked about that yesterday, how in some subject areas you think you have the right answer, and then you get your test back and you go, oh, well, I guess that wasn't what the teacher was expecting. But that rarely happens in math class. It's not like I can say, well, I don't think 2 + 2 = 4. It's very certain. So there's a lot of sort of concreteness to mathematics, but the world is full of patterns, okay? There are patterns all over the place. And we, as humans, are very pattern related. We like patterns. So, for example, if you take any circle in the world, no matter how big or small that circle is, and you divide its circumference by its diameter, you're always, no matter what the circle, going to come up with the same number. And it's the number pi, okay? That magical number will always be the case. So there seems to be this like mathematical nature to the world and the universe. Galileo actually said that nature is written in the language of mathematics, okay? So I would argue that mathematics is more important now than in the time of Galileo. That being able to use math for jobs, for life, is way more important now than back in Galileo's time, where you could just dig a ditch and you could make a life out of that, okay? So it's this certainty and usefulness of mathematics that makes it an important study. A philosopher and mathematician named Bertrand Russell said that when he started studying geometry at the age of 11, he said it was one of the great events of his life, as dazzling as his first love. He had never imagined there was anything so delicious in the world. Now that's a little extreme, all right? I'm not here to argue that I'm that, quote, into mathematics as Bertrand Russell was, but you can see how some people can really take mathematics and take it to heart, okay? Okay, so like for some people, I don't think you've ever used the words love or delicious when you were talking about mathematics. Maybe you have, I don't think so, but maybe you have. So for some of us, we like how math makes us feel certain, right? I never really liked writing essays when I was in high school because my high school, it was a history teacher, I thought didn't like me. And I didn't like him either, I'll be honest with you. And I thought he had it against me. And I thought, even though I wrote a good essay, I thought he was giving me a bad mark just because he didn't like me. But I never thought that about my math teacher. Well, he may not have liked me, but I never knew he was going to mark me bad because I knew there was that certainty in mathematics that he couldn't escape. I knew that if I made a mistake in math, someone could show me the mistake. They could say, here's what you did wrong. And I could go, oh, okay. And I would get that. Whereas with an essay, I would say, well, they'd say, well, I don't think you should have written this. And I'm thinking to myself, well, wait a minute, I liked writing that. Why do you think I shouldn't write that? Or even worse, poetry. I always thought I was good at poetry, but I did terrible at it. My wife has since corrected me and said, no, you're terrible at it. But nonetheless, I liked the certainty of math, okay? But not everyone does. Some people find math very, very threatening, okay? They think that math is incredibly intimidating, really hard, and they, quote, just don't get it, okay? So we have those two extremes as math teachers. We have students who love its certainty and students who are intimidated by it, okay? So I ask you this simple question. You don't have to answer. It's just something to think about. Do you think that people who do well in math, like who have a good mark, like math? In other words, have you ever encountered someone who hates math but has a great mark in math? And vice versa. Someone who loves math but has a bad mark in math. Do you think there's a correlation there? What do you think?
Well, I usually have a really good mark in math, but I still really don't like it that much.
Okay, so it is possible. Is it probable? Right? Is it the case that that's usually the case? Just something to think about. Okay. Now the other thing about math is you have to have what's called selective attention. Okay? Here's the way it goes. When you guys were little babies, your parents or someone put in front of you an apple. And when you were first starting to talk, and they said, "What's that?" And you said, "Apple." And then they put another one there, and they said, "How many?" And you'd say, 2 apples. Then they give you 2 more, and they'd say, "How many?" You'd say, 4 apples, right? Then they take the apples away, maybe, and they put some little toy dinosaurs, and they put 2 there, and you'd say 2 dinosaurs. They'd put 2 more, they'd say 4 dinosaurs. And this was fun when you were a baby. Eventually, they stopped putting stuff in front of you. There was no more apples and no more dinosaurs. They would just say to you, "What's 2 plus 2?" And you didn't say, "2 what?" Whereas as a baby, you would have said, "2 what?" You just made what's called the leap of abstraction. You now went from just thinking about 2 things in front of you, like 2 apples and 2 to just 2. Well, what's 2? 2 is a concept. 2 is abstract. There is no such thing as 2 unless we apply it to something like the apples and the dinosaurs. And the fact is, math has gotten more abstract year by year. So when you first started in kindergarten and then went to grade 1 and then all the way up to last year in grade 8, math kept getting more and more abstract. You look ahead to, say, some of what my grade 12 IB students do in mathematics. Extremely abstract. They use something called imaginary numbers. And they're literally that. They're just numbers that are imaginary. They're not at all real. So that's what's happening. And where that tends to happen is that tends to lose kids. Some kids get lost as it gets more and more abstract. And I hear that from students. They say things to me like, "I'm never going to use this. This math doesn't make sense because it doesn't actually, I can't actually feel it. I can't actually do anything with it." So it's something to keep in mind. You're not the only one if that's the case for you. And what my job is to try and pull that back so it actually has something real for you to actually feel like it does. Now at the same time, have any of you ever encountered this? There's these people who are really good in math who have a little bit of, I'm just going to say, snottiness to them. They act like they know what's going on. It's like they have this secret that you don't. Now, it's not always the case. I hope it's not the case for me. But it tends to also do that because they often know that people who have trouble with math aren't making that leap of abstraction. They're not getting it. And so again, I'm not big on that either. I think that's terrible, right? So we may know that life itself is way more important than what you can write down in numbers and symbols. There's way more to life than that. But so I just want to start with that little bit of philosophical thought. Okay, now to the content at hand. Let's start with this. These are simple questions, 3 simple questions to start today's lesson. Who thinks they know what a rational number is? Take the word, break it apart, okay? What do you think a rational number is? Go ahead, just say. Sure, yeah. What's another word rational you can think of? Ooh, a non-whole number. Take the word rational, take the root word of it, like pull the end part off it. What do you get? Ratio, right? What do you think? Like a common number, yeah. What do you guys think the word ratio? When you hear ratio, does that mean anything to you guys? Fractions. Comparison, yeah. Comparing things, sure. You're on the right track, absolutely. So here's what we've got. We've got numbers that are pretty common, numbers that might be in fractions, numbers that compare to other numbers. All of these seem like really good answers. We'll come on. So it's kind of a very general definition, but you're in the right ballpark. Now, what's an opposite number? What would that mean? What do you think?
Like a regular number, like just one or two, because a rational number probably has something to do with fractions or decimals.
It could, but let's ignore the word rational for a sec. Let's just say opposite number. What do you think? Negatives and positives. Wow, that's a great idea. Okay. So if you have a number, you could have an opposite of it. And then finally, what do you think the word equivalent means? It's the same. It's equal. Absolutely right. You guys know this stuff. That's good. Because again, what sometimes happens in math class is you get hit with fancy words like equivalent, which all it means is the same, right? So be careful that you're not overthinking things. Sometimes the words just mean something simple. Okay, so let's take a look at this idea of the rational number system. Okay, going back to that history lesson, you're little babies, okay? The first set of numbers that you learned as little babies are called the natural numbers. When you first learned to count, you started at 1. You may even watch video of your parents took of you as a little baby learning to count, you started at 1. And as a parent myself, I know when your kids are really small, you get excited when they can count up to a certain number. Imagine if I gave you that assignment right now. Count up to the highest number you can count to. It'd be a horrible assignment, wouldn't it? Yeah. But at one point in your lives, that was something that your parents did with you. They had you count up to a certain number. But you always started at 1. And that's the natural numbers. They start at 1 and they go up to infinity. The idea of 0 happens a little bit later. 0 is actually a little bit more of a complicated concept. So to add 0 to this means we're no longer in natural numbers anymore. We're now in what's called the whole numbers. Okay? The whole numbers include 0. Okay? Now, once you got past that, and probably when you got to school, although maybe you had super keen parents, but probably when you got to school, you learned about something called negative numbers. Now that you've got all these whole numbers, and you add the negatives, now you have these numbers that we call integers, and I'm sure you've heard that before, okay? And with the integers now, you go from 0 up to positive infinity, and from 0 back to negative infinity. You go both ways, okay? So a way you could sort of look at it as well is that rational numbers are the ratio of integers. So in other words, 1 over 2, or a half, is a rational number. 2 over 3 is a rational number. But as well, you could put 2 over 1, which is 2, so 2 itself is also a rational number. So rational numbers include lots of stuff. It's not just fractions. It's whole numbers, negative numbers, 0, all of it is rational numbers, okay? Because what rational numbers really are is they include those whole numbers, they include the integers, and they include the in-betweens. So like what's a number between 1 and 2? 1.5. 1.5, right. That's a rational number. Someone said it a different way. Someone said 1.5, someone over here said 1.5, which is the same thing. And if they're the same thing, what's a fancy word for that? You guys are on the ball, okay? That's correct. Now there are numbers that are what are called irrational numbers as well. That's another leap of abstraction that you don't have to make this year, luckily. But for those of you going into even more advanced math, you're going to learn about what those are. Irrational numbers are numbers that aren't easily set. Well, I can give you an example of one. Pi, right? Pi technically has no sort of end to it, and it's an irrational number. Okay, so here's the way it looks. You started with those rational numbers, or sorry, those natural numbers Then you learned about whole numbers with 0, and then eventually became integers. But they all encompass one another, right? Integers are natural numbers. They're the same thing. So it's sort of one way to look at it. Okay? Now this was, again, just an opening intro. Doesn't really relate, because remember I started by showing you guys what's on the curriculum? This is kind of a little bit of background. Now let's dive into a little bit more specifics of the curriculum. Okay, so here's what is the formal definition of a rational number. It's a number that can be expressed as a over b, where a and b are integers, and b cannot be 0, because we can't have a number over 0. Okay? Examples of rational numbers include -4, 3.5, -1.5, 1 3/4, and 0. All of those are rational numbers. So the idea of a rational number is it's lots of different examples. Okay? When they are equivalent, they are the same. Now, let's get a little trickier. 24 over -4 and -18 over 3. Let's just take those first two. How are those equivalent? How could they be equivalent? They don't seem to be equivalent. Does anyone have an answer to that? Back corner. Right, right. Let's take a look at the picture down here, this picture. If you were to tell me what that would be as a fraction, what would you say it is? 1/3, sure. We'll just go with the blue. Because remember, the way, maybe I'll draw this out for you real quick. Where is it? Okay. So the way you can think of fractions, and I'm sure you've done this before, is as it was shown in that circle diagram there, okay? You're using a line, and the number on the bottom represents how many pieces there is to the whole. So how many pieces are in that whole circle? 3 pieces, right. If I was to say I'm just talking about this piece, that's one of the 3 pieces, right? So when I say what's that as a fraction, it's 1 over 3. That's what it represents, right? It's one of the 3 pieces of the fraction. Okay, good. So what would, if this is 1 over 3, what would this one be? No, how many pieces are there? Right, there's 6 pieces. How many are in that bluish color? 2. So there's 2 over 3. But are these 2 the same? Like if I asked if this was pie and I said you get to eat the blue pieces, would you get to eat the same amount? Yes. Absolutely, yes. Yeah, I'll take the red, yeah. So they are equivalent. So that's why if you look at these fractions, they are actually talking about the same thing. They are equivalent, okay? Now, it gets a little more complicated. If you look at this one right here, now we're dealing with those negative signs. And again, some students can have a little bit of trouble with that. So we're going to try and work through if you have any trouble with that. But believe me when I say all 4 of these represent the same amount. They are equivalent. And the amount is -6. The answer to all 4 of those is -6. Don't worry, we're not going to spend time calculating it. But it's something to keep in mind. Okay, so here's a problem. Let's try this problem. I'm going to put these numbers here, and I'm going to say to you, I want you to put them in order. -1.2, 4 over 5, 7 over 8, -0.5 repeating, and -7 over 8. I say, this could be a question on your final exam. It says, put them in order. Okay? So the first thing I'm going to do is I'm going to do some estimates. Okay, estimation sometimes is a useful skill, just to get a grip on it. Well, -1.2 is kind of like just -1. Let's just forget about the 0.2. Just say it's -1. And 4 over 5, well, 4/5 isn't 1, right? If I have 4/5 of a pie, I don't have the whole pie, so it's less than 1. So I know that 4/5 is smaller than -1.2, and I'm just estimating at this point. And 7 over 8 is also a little less than 1. And -5 repeating is a little bit less than just -0.5. And -7 over 8 is a little bit more than -1. so I could kind of estimate the order by just sort of being quick about it. And sometimes that's a good strategy when doing math. It's like, well, I'm just going to try to guess and see if that works. But if it's a test, I want to kind of be sure. So what I might want to do is get a little bit more of an adept strategy. So maybe I'll draw out a number line. Okay? And I know that if I go from 0 down to -2, if I just go up to +1, that should cover all the numbers I need. So the first thing I can do is I can put -1.2 on my number line. Go -1.2. Good, that's on the number line. Now I get to a fraction. In order to use that fraction on this number line, maybe what I should do is convert the fraction to a decimal. Does anyone know how to do that? How do I turn a fraction into a decimal?
You would multiply it.
Not multiply.
Divide.
Divide, right. Divide what? The top by the bottom. Who knows the fancy word for top and bottom in a fraction? What are they? No, so, you. Yes, ma'am. Numerator and denominator. But don't try and be fancy. It's the top and the bottom, right? You guys got this. Okay, so that's where 0.8 would go, right? 0.8, it's positive. 7/8, I could do the same thing. That one I wouldn't have you do in your head, but that's 8.75. Now I know that's a little bit bigger than 8, right? It's getting closer to 1 at that point. Then 0.5 repeating. Well, I can put that on my number line. I know where that is. And -7/8, I can also do, it's going to give me the same answer as up here, but this time it's on the negative side. So I'd put that on my number line. And as a result, now I have my order, right? The order you can see is right there. It's easy to see where everything goes. So it's a useful skill sometimes to be able to go back and forth between those decimals and fractions. And we'll talk more about that in a second. Okay, here's another problem. Which is bigger? This one or this one? How do we solve this? Well, again, to work with these fractions, we're going to need equivalent fractions, or in other words, something with what's called the common denominator. And again, I hope this is a term that you guys are familiar with. So the common denominator between 4 and 3 is 12. So to convert these to a common denominator, I have to take that 4 and multiply it by 3, and whatever I do to the denominator, I do to the numerator, multiply by 3. So now I have -9/12, and on this side I have to multiply by 4, and I get -8/12. So which is bigger? Just a minute. Think, stop. This is a trick question. I'm trying to trick you. Which is bigger, -9/12 or -8/12? Back corner, or back middle.
It's -8/12.
That's correct. Does everyone know why? Because it's close. Yes, that's correct. Okay? Very good. Okay. To remind you of that, the quotient, what does quotient mean? That's a fancy word.
The quotient is the answer to division.
The answer to division. And is a fraction and division kind of the same thing? So if I have a fraction, like 8/12, the quotient would be what happens when I divide the two, right? So quotient is kind of still, it's all in the same ballpark, right? So again, we got to watch out for negative signs here. Some of you, again, get a little confused on the negative signs. So notice here, I can put the negative sign here, or up here, or down here. They all mean the same thing. Same with this one. Notice I can put the negative sign in different places. It's still going to mean the same thing. Okay? They're all equivalent. Okay. Now, that we have the denominators the same, like we did there. You guys were correct when you said that -8 was greater than -9. Sorry, I forgot to put the negative sign there. So the answer is -2/3 is the bigger or the greater fraction. Now, another way we could have done that is not to bother with the common denominator. We could have just made a conversion to decimal. So if I did that, I'd get -0.75 and -0.6 repeating. Which is bigger? Well, the answer is -0.6 is bigger because it's, again, closer to the positive side, and you'd get the same answer. So there's two different solution methods for the same problem. One is working with fractions, one is working with decimals. Okay, here's another problem. This could again be an exam question. What's a fraction between 0.6 and 0.7? Well, if we put it on a number line, 7 and 6, they're right beside each other. But again, here you'd want to be converting those decimals into possible fractions. So I know a number between 0.6 and 0.7 is 0.65. Right? That's in between those two. But what's 0.65 as a fraction? Well, I can just put 65 over 100 to make it a fraction. Now I could reduce it from there. I'm not going to, but I could reduce it at that point. And now I'm starting to use words that I hope for some of you you're comfortable with. When I say reduced fractions, when I'm talking about converting. But what I also want to sort of get out of this is why I'm kind of starting with this stuff here is, if you are uncomfortable with working with fractions and decimals, now's a good time to let me know. Well, not right now, but it's good to kind of get an idea so that next week, maybe I need to spend a little more time on fractions for some of you. For some of you, clearly not. Some of you seem to grasp this. Okay, so let's talk about decimals for a minute. What is decimal form? What does that mean? Well, it means a decimal. Now, these are kind of rhetorical questions. I don't even really need an answer from them. How can I add and subtract decimals? Like I said, 0.735, like if I give you a big decimal number and another big decimal number, do you know how to add, subtract, multiply, and divide them in the easiest way possible? What would be the easiest way?
Keep your decimals in mind.
What's an easier way than that?
Oh, use a calculator.
Use a calculator. Yes, why not? You can do that too, right? But both are right answers, and yes, calculator is useful. But one thing I find grade 9s trip up on is, especially if you've just got a scientific calculator, is how to work with negatives with a scientific calculator. So I'm going to put something in there. If you have your calculator with you today, you may want to just pull it out to make sure, if you've never done this before, how do I make something negative? Here is one of the possible buttons that could be on your calculator. I'm just going to turn the light up here for a little bit just so you can see. But it's possible, but the button on your calculator will look like any of these first four with a little plus minus. Sometimes it's above, sometimes it's beside, sometimes they have a little slash. But another key that it could be to make something negative is that one. What it's absolutely not, is the subtraction key. That is not the same. Okay, that is not the way to make something negative. Okay? So find that key on your calculator if you haven't, because it's useful to you. It's useful when doing these problems with a calculator. You know how to operate it. And we'll try an example of that in a minute. Okay? The other thing that might be useful to you on your calculator is the ability to work with brackets or braces or parentheses. All those words mean the same thing. So for example, negative 4 times 1.5 is the same as, is equivalent to, negative 4 bracket 1.5 or parentheses 1.5. Now, this can get tricky now. If you look at this problem, 2.65 plus bracket negative 3.81. Don't read ahead. Don't read ahead. Try not to. What's another way I could have written this question? It would have been equivalent, would have been the same.
3 plus multiply negative.
No multiplying going on there, yes. I'm not sure. The answer I was looking for is 2.65 minus 3.81. That's it. That would be the same thing. They would be equivalent. If I'm adding a negative, it's like adding the opposite. It's the same as subtracting, right? It's kind of the same idea there. So here you can see in the estimation, I'm saying, well, it's around 2.65 is almost 3, and 3.81 is almost 4. So it's basically like 3 plus negative 4, which is really the same as like 3 minus 4, which would be negative 1. So the answer to this is going to be around negative 1. Then I'd actually punch it in to my calculator, and I'd get negative 1.16. But how I punch it into my calculator is something that you should get useful to. So here's how I would do it. I would clear my calculator, I would type in 2.65 plus 3.81 and then press the plus minus key. What that does is it makes that one negative. On some calculators, you can press this first, but I wouldn't recommend it. I would try it out on your calculators, what I'm saying. Get used to the way your calculator works. Okay? And then there's another problem that basically works out the same way. But getting used to your calculator is something that you should be aware of. So it's not like a test time and you're trying out that calculator for the first time. You're like, got your hand up, Mr. Walks, I don't know how to make this number negative. Of course I'll help you, but it shouldn't be during a test for the first time. That's something that an assignment is good for, to work out the kinks on your calculator and get used to it. Okay, now, I just wanted to stop for a second here. Again, some of you might be getting lost at this point with this whole idea of negatives and positives and how they all fit together. Am I the only one, or is other people thinking that sometimes? So let's try a technique, a memorization technique. Do you guys like memorizing things? I don't. I hate memorizing things. But it's useful, right? Sometimes it's useful. Okay, so let's try something. Let's try this. Maybe you've had other teachers try it. Let's memorize a sentence, just one sentence. Piece of cake, right? One sentence. The sentence is a negative times a negative equals a positive. Now, here's what I want you to do. And this is actually what's called a mnemonic memory device. Okay? My wife has a degree in psychology, so she often tells me this stuff. She says that, and this is actually a tip for the dating world for you guys. I don't know if you're going into the dating world or not, but I'm going to use the fellas as an example. Fellas, if a girl introduces herself to you, and then later when you talk to her again, if you get her name wrong, you're not off to, ladies, that's probably not good, right? I'm guessing it's probably not good. If she says, hi, my name is Sarah, and then later you say, oh, hi, Serena, right? Like, that's not, it's not going to work out for you. So it's good if you know her name. She'll be impressed with that. Okay, here's a technique. If you repeat her name back to you when she introduces herself, you have a 5 times better chance of remembering it in the future if you say it out loud. Because very often they'll say, hi, my name's Sarah, and you just go, hi. But if you say, hi, Sarah, you'll have a stronger chance of remembering it. So by actually saying it out loud, you have a way better chance of remembering it. So when I say I want you guys to memorize this sentence, I want you to say it out loud. Now, don't pretend like it's O Canada and mouth the words like you did when you were in elementary school. I want you to actually say it out loud. Now, I'm not done yet. It's also said that if something embarrassing happens to you, you'll have a better chance of remembering what occurred on that day if something embarrassing happened. So can I have everyone please stand on a chair in the room right now? Oh, it'll be good for you to get up and stretch a little bit. Stand up on a chair. All right. This is embarrassing, right? Well, not for all of us. It's all right now. And now I want you to, out loud with me, say I'll say it out loud first. A negative times a negative equals a positive. Okay, so let's all do it once together. Ready? 1, 2, 3. A negative times a negative equals a positive. That was 1. That was pretty good. Now let's go for number 2, and let's bug Mr. Rohringer, who has a class next door, by being really, really loud on this one. Ready? Really loud. Ready? A negative times a negative equals a positive. That was pretty good. On our third try, I don't know if you know German. I don't care if you know German, but I want you to do your best German accent for number 3. You're going to say it in the German accent. A negative times a negative equals a positive. Like, like Arnold Schwarzenegger kind of a guy. Ready? Ready? No one did it with me. Let's all do it together. Ready? A negative times a negative equals a positive. And now we only have 4 more to go. Let's do them all quickly. Ready? Together. All 4. A negative times a negative equals a positive. A negative times a negative equals a positive. A negative times a negative equals a positive. And a negative times a negative equals a positive. Please carefully get down. Okay. Hopefully, if you're sitting at a test and you're stuck, you'll remember this day, this stupid day, where the stupid math teacher made you stand on a chair. And that sentence will pop in your head. And when it pops in your head, you'll think, well, how can I interpret that? What does that mean? Well, hopefully you'll remember that it means a number of things. It means that If you times a negative by a negative, you'll get a positive. It'll also apply to division. If you divide a negative by a negative, you'll get a positive. When a positive is multiplied by another positive, well, you're not even going to have to worry about that. I'm not going to say 2 times 2. You're not going to think -4. You're not going to think that. The only time it's different is when you multiply a negative by a positive, you'll get a negative. So I could have written all this up here and had you memorize it. But instead, I just think just one quick sentence might be just the one thing you need to get past that sometimes. That and practice. Okay. So I am watching the time. We're running a bit long, and that's okay. If I don't happen to give you the assignment today, I don't think you guys will be that upset. I don't think you'll be that upset with me if I don't give it to you. So keeping me talking is probably not the worst idea in the world, but let's keep rolling here, okay? So if we're working with fractions, okay, we're working with fractions now because this unit should have you work with some fractions. You should be comfortable with that. If you're not, please, at some point next week, tell me, Mr. Walks, I could use some help with fractions. Please, I'm going to go technical on you guys. You know what? If you're too embarrassed right now to say, Mr. Walks, I'd like some extra help with fractions, on the weekend, grab a computer, email me. Mr. Walks, how about some extra work with fractions next week? 18? Anyone on 18? Okay. And I'll do that. I'll slip in some extra work on fractions next week. Okay? So when you think about things like common denominators, when you think about things like mixed numbers and improper fractions, if that's stuff that you didn't, because I know you did it in grade 8, you know, you even did it in grade 7 and 6. If that, and I know that because my daughter's in those grades, you got to kind of let me know. Because otherwise you're going to get confused again. And I shouldn't take for granted, I should because you've got a credit in those courses, but I want to make sure that you're comfortable with fractions. Okay. So now, hopefully just using that sentence is a way to apply it to things like problems. So let me just step back here. Here's the problem I'm talking about. 4 over 10 minus bracket 1 over 10. What do I have happening here? I have a negative here and a negative here. What was the sentence? So could that be applied here a little bit? So what's another way I could write this without negative signs? How? Close. What's another way? Well, I don't need the answer. I just need to sort of another way to write this. Yes, what's another way?
Just take out the negative.
And what would you be left with?
Just the regular.
A positive. No, because a negative equals, so a 4 over 10 plus 1 over 10 would be a way to write it. Now that might be confusing to you again, but it's going to take practice, but that would for sure be a way. Now what's 4 over 10 plus 1 over 10? It's 5 over 10, which is 1 over 2, if we reduce it, or a half. So these are the kind of problems that, again, I want you to kind of practice. These are tricky ones. I put them up there on purpose to be tricky. Okay? Similarly, you should be able to work with mixed numbers. Now, who knows how to work with mixed numbers? There's techniques. You don't have to answer, but I'm just saying, hopefully you have some techniques for working with mixed numbers. Okay? I tell you what, let's stop there. Let's stop there for today. Oh, no! Just one sec.